Good afternoon. It's 3 o'clock here in Denmark now. My name is Paul Andersen, and I'm going to give you this webinar here for the next hour concerning ARTeMIS Modal, Operational Modal Analysis. Today I would like to talk a little bit about how to use ARTeMIS Modal to make multi-setup testing of a structure. I'll come back to what multi-setup testing means, but this is, you would say, the topic of today. Besides that, I would like then to try to go through some of the things that we should make sure are okay. That is the data that we are going to collect. That is that it in fact is of a quality that allow us to do a decent analysis using the different tools in the software. Then I want to show you a couple of our methods that we have in the software package. And then finally we'll give some remarks and conclusions on this. I will switch a little bit between PowerPoint presentation and then doing some testing here on a structure I have next to me on a table here. And then, of course, using the software also for this approximately 1 hour presentation. So this is the idea of this webinar here. We will start a little bit, you would say, light, just trying to explain what modal analysis is, and then how we can actually make different types of modal analysis depending on what we have available. If you start by looking at a very simple structure, we could imagine some kind of slender structure. It could be a chimney or a high-rise building or something that is affected by some kind of excitation that makes this structure here vibrate with a mix of the different dynamic modes that it has available, this structure here. So if we magnify, you could say, the vibrations that we can observe, it may look something like this at a certain time during the measurement. Normally what we will do is we will put some sensors on different locations on the structure and then measure these discrete points in one or more directions depending on the type of structure that we have. And once we have then gathered this data here, these measurements, these are now, you would say, a physical representation of what's going on this structure here. We are measuring, for example, accelerations. It could also be velocity, or it could also be displacements, or even strain can be measured in different locations. And that will then allow us to look at this set of time series that has been recorded simultaneously. That will tell us something about how this structure here is behaving in the physical domain. So this is where we are now. We are here in the physical domain over here. But if you really want to get into the details of what you could say the dynamic behavior of this structure here is, we would have to dive in behind these the overall physical vibration pattern that we measure, and then look at the specific modes of vibration. And these mode of vibrations are described by a set of parameters. There is a set of mode of vibrations, and there is within each of these a set of parameters that describe the individual mode of vibration. The most visible one that I'm trying to illustrate here is the mode shape. So the mode shape of a slender structure like this, the first mode, or the mode shape of the first mode of bending, would be some kind of very simple bending back and forth of this structure here. This is the mode shape we have here. It's actually a parameter. It's not a parameter. It's a vector of parameters that is describing this particular part of the mode. There are as many parameters in this vector here as we have measurement channels available. The other parameter that we have is the one that describes how fast this mode likes to vibrate. It's the resonance frequency, basically, that we are talking about here, and that's, we also call it the natural frequency. and it's measured in hertz, 1/seconds. And besides that one, there is another one also we call the damping ratio. The damping ratio is the parameter that tells us something about if we are giving this structure here a hit and it can die out, how fast will it die out then? The more damping we have, the faster it dies out. So a lightly damped structure is a structure that keeps on moving for a long time, whereas a heavily damped structure is one that dies out very, very soon. These are the parameters that we're looking for when we do mode analysis: natural frequency, damping ratios, and mode shapes. There are two different ways basically we can find these depending on how we can test this structure here. I'll come back to that, but one of them is the more classical one is called experimental modal analysis. The other one is the one we are going to talk about today is operational modal analysis. There are these two different ones, but ultimately it's we are doing these different types of analysis, modal analysis, to end up with the same sets of parameters. There is one, you could say, difference between the two. You can get a little bit more if you do experimental mode analysis. You can get actually the actual scaling of the mode shape, but this is not something that normally is important in many applications. It's normally more the shape of the mode shape, and then also, of course, the two other natural frequency and damping ratio that is of importance. And that's why operational modal analysis in many cases is actually a very desirable tool to use. There are three different ways you can analyze data. You can do it in the physical domain. So if you are trying to look here, what's happening actually in the physical domain, if I now try to look at a specific frequency, but in the physical domain, I will be looking at something we call an operating deflection shape at a certain particular frequency. I can also look at what happens over time. How did my structure move? What type of displacements did I have during a certain time of my measurement? Then it will be time domain operating deflection shape analysis I will be doing. So in both cases, I'm studying what's going on here with the physical domain. You would say representation, which is the raw measurements that we can obtain from our data acquisition. Then if we go to the other part here over here where we're doing the modal analysis, where we are separating the different modes of vibration from one another, we then have the two different ways of doing it. We have the experimental modal analysis, where we need to measure input and output, and we need to make sure that nothing else is affecting our structure while we're testing, except the input forces that we are actually supplying. And then we have the operational modal analysis, where we are just measuring the responses that are caused by some vibration that we don't really know what's coming from. We are not measuring the actual input, only the output in this case here. So you can say to do experimental modal analysis, we have to switch off everything else. If it's a machine that is rotating, we will have to turn off the machine while we are doing the testing. Whereas if you're doing it with operational modal analysis, we can leave it running and then look at how the structure actually behaves during its operating conditions. So this is the major difference between these two different ways of doing modal analysis. And this is also what I'm trying just to explain with this very simple drawing here. We have a structural system here. We assume that it's a linear system, which means it doesn't really matter if we are exciting it with a very weak excitation or really, really strong excitation. The structure should behave in the similar manner, and the parameters that we can extract, the mode parameters, they should not really be dependent upon what level of excitation we are supplying. What happens is when we're doing experimental modal analysis, we are exciting it with some measured excitation, and we can then also measure how it responds to this in certain locations, the locations we normally want to find the mode shape in. And with the input and output measurements, we can then extract the modes based on estimation of something we call a frequency response function. This is another topic. I will not go into more details about it, except that we really need to make sure that we can measure all the excitation and of course how the structure responds to it. All this has to be measured to do this type of analysis here. We like to extend this a little bit so that we get some more flexibility. You can imagine if you have a large structure, a bridge or dam or offshore structure or something, standing out in Mother Nature, being excited by natural excitation, it is simply impossible for us to switch off all these different types of excitation and then start using a small impact hammer like the one I have here to excite a large structure like that. We need to make use of what we have available of natural excitation in order to be able to analyze a structure like this. And this is where operational modal analysis comes into to play, you could say. And to make it work, we have to, you could say, put a kind of a stochastic framework, you could say, another kind of way of thinking than what we did in the experimental modal analysis, where all the things are measured and assumed to be known. Here in operational modal analysis, we have many unknowns, and we have to, you could say, be able to work with that. And the way we do that is we make some assumptions. First of all, let's look at the structural system. We first of all assume it is the same system as it was with when we did the experimental modal analysis. We assume it's a linear structure. We also assume that it's time invariant. That means it's not going to change its behavior during our measurement. It has to be constant during the time we are measuring. Otherwise, we cannot really use this type of analysis here. But based on these two assumptions here, we have what we can define as a structural system that we can actually work with and we can analyze, get modes from. We can still put some sensors that can measure the response on the structure. You can imagine a bridge. You can put some accelerometers on the bridge girder and measure what's going on, the response of this particular structure in these points. So we are still able of actually measuring response. The problem is we cannot really measure the input. Input is difficult because it's all kinds of sources that are exciting the structure at the same time. And this is simply impossible to measure. So we have to assume something. We have to assume that these unknown excitation sources here, they are having some kind of distribution, some kind of way they look, you could say, if you look at it in frequency domain. And what we do is we assume something we call a Gaussian white noise. We assume actually that everything can be modeled based on a Gaussian white noise, which in frequency domain is a kind of a spectrum that is completely flat at all the frequencies that we are looking at. So if we can assume that or something related to that, then we can do operational modal analysis of the response we are measuring of this linear system here. Normally, you could say the excitation is not completely flat over the whole frequency range. There might be some parts where you have more energy than others. You can imagine a wind spectrum, for example, where the wind is exciting the structure, that is distributed according to some wind spectrum. Here you will have some wind speeds where you have more energy than others. So the frequency content will not be the same along the whole frequency range that we are measuring. And to actually accommodate for this, we insert a kind of a additional shaping filter or excitation filter. So you can say we excite with our flat white noise. This shaping filter here will then shape this into whatever distribution we actually have at the time of measurement. And this is then the unknown excitation forces that are acting on the structure during the testing. This is the assumptions we do. it is not because we have to go out and measure and figure out what this shaping filter is or anything, but it's just our way of thinking to describe why does it actually work, what we are doing. So you can imagine there will be something when we do the analysis that relates to the structural system, but there can also be something that relates to the excitation system, you could say, if this is not a completely flat excitation that has been supplied during the testing. So the art of operational modal analysis is to find both these and then filter out, you could say, the structural system part that we actually are interested in, and then leave out the other part that we don't care about so much, at least. This is the concept, this is the paradigm we are working in when we are doing operational modal analysis. It's a little bit more complicated than the more classical input-output modal analysis. So we can just go and just grab up these assumptions here. We can imagine that we have to use input forces that are stationary, but then they are approximated by filtered zero mean Gaussian white noise. It's very complicated. But if we can assume this, it means that our response will be Gaussian distributed. And if something is Gaussian distributed, we can fully describe it with the first and second order moment, which means in our case, we can actually describe it completely with either looking at the correlation function of the measurements or looking at the spectral densities of the measurements, because these are the second order moments. And this is why it's very desirable to assume that everything in this way is Gaussian, because it allows us then to use, you could say, spectros, which is, you could say, what we prefer to use, because it just makes it very intuitive and easy to look at what's actually going on in the structure. In the practical, you could say, parts or sense, there are these three things that we basically have to take care of. First of all, we have to make sure that when we are doing some kind of measurement on a structure, there has to be some kind of broadbanded excitation available. The worst thing one can do if you want to do operational modal analysis, that is to go out with some kind of shaker that is only shaking at a certain frequency, a sine wave like that. Maybe it's providing a lot of, you could say, force at this particular frequency, but it's not exciting anything else except what's going on around that frequency. So that type of excitation, what we call narrowband excitation, is not good for operational modal analysis. We need something that is broad, something that can excite all the different modes that we have in frequency domain in the range where we want to find modes. So it's really important that there is something broadbanded that can excite the modes that we are looking for. If it's not the case, it can be very difficult to find, you could say, high quality modes. I would nearly say impossible. So this is a very, very important assumption for practical use of operational modal analysis. We also need to make sure that whatever is exciting the structure is actually exciting the modes that we are looking for. If you want to find some, let's say, high frequency modes on a large structure, it can be difficult because many times the natural excitation that you have, wind, microtremors, waves, and whatever it can be, they tend to excite the low frequency modes very nicely. And then the high frequency parts is a little bit more not so well excited. And that means that you can have troubles finding the high frequency modes in a case like that. So you have to make sure that whatever you are looking for actually is excited. It can be that you have broadband excitation, but maybe this broadband excitation is only exciting the low part of your frequency range, and the high part is not so nicely excited. So this is something that also you have to take into account, and if it's a large structure, there might not be much you can do about it except accepting that the high frequency modes, they might not be so well represented. The good thing is that normally it's easier to actually estimate high frequency modes because you have much more information because of the high frequency content of the high frequency modes than the low frequency modes. So a kind of a compensation happens there. You don't have so much excitation perhaps, but on the other hand, you have a lot of cycles of the high frequency modes available in your measurements. So that's a compromise, you could say. Finally, it's also important that you actually have multiple independent input sources. Because if you have multiple excitation sources acting on the structure, you basically then get a Gaussian distribution of your response that you are measuring, and you can also probably imagine that it's easier if you can you are hitting the structure in different locations, different directions. The different modes, they can better come to life and be extracted in the end. So it's actually very important that there are multiple input sources. I will try to come back to that a little bit later so we can see, you could say, the difference between having one or having many. Let's go now to, you could say, the real topic here. That is, what should we do when we have limited amount of sensors and we would like to know the mode shape in many points of the structure that we are measuring? This can be, you could say, a challenge because let's say you only have 10 channels available, but you would like perhaps to know the mode shape in 100 points, degrees of freedoms, we could call it. What to do then? This is where we have to now make a little bit, you could say, clever use of the sensors we have. Of course, if we have plenty of sensors, it's not a problem because we just put them on the structure in the points we would like to know, and then we do a measurement, and that's it. Then we will have all the different mode shape degrees of freedom estimated in a single analysis and measurement. But when it's not the case, we will have to use something we call multi-setup testing. And this is what I'm trying to show here with this little car here. It's in operation, as we can see, but during that operation, we are trying now to find the mode shape in many points. We basically only have 5 channels in this little demonstration here. And you can see that there are 3 channels located here. These are the points where we would like to know the mode shape. But in order to do that, if you also want to find these 3 points here and these 3 points here, we need to merge these 3 parts together in some way. And to do that, we need some common reference information. You can imagine that you start measuring this part here. You get as a part of your mode shape then for that. Then you move your sensors to the next part here and you measure that also, and so on. And you get small pieces of the mode shapes that you now have to put together to get the complete mode shape afterwards. In order to do that correctly, we need to have something that we measure every time in same points and directions and so on. We need something we call reference measurement. To do that, we have to actually put some sensors in some locations and keep them there. So you can imagine these 2 sensors here, they are put there and we keep them there all the time. We start putting the 3 first sensors in the locations where we like to know the mode shape. All these 5 sensors are now measuring what's going on. Then we move the 3 sensors to the next location, keeping the references at the same location, and then we start again. So that means every time we have a new measurement, we have 3 channels that are new, but we have 2 channels that are measuring in the same location every time. And based on that, we can now extract a mode shape piece every time for these 2 sensors here. And that mode shape piece should be the same for all these 3 measurements that we have been doing in this case here. But they are probably not, because if you have a vibration level that suddenly raises or falls from one measurement to another one, these mode shapes here, parts here, they will not be the same. They will also change level. If you look at it, absolutely, the level of vibration. But we have then, you could say, the shape of these two here, that we have to end up having the similar kind of information for all 3 measurements that has been done in these 2 locations here. And then we're using some least square technique to actually estimate the relation between one measurement and the next one and the next one again, so that we can end up actually having, you say, kind of a parameter that we can multiply the different parts with, so that they now end up with the same level. And we then get a global mode shape in the end that looks good. That means it's really, really critical what we have here, because this is actually what enables us to put things together in a nice way. So that means, first of all, we need to make sure that we have really high quality sensors working here. You should not just take the most cheap strain gauge or something and put here, and then use some nice quality accelerometers in the other locations. Then you will really get some bad results in the end. You will get each of the parts or pieces of the mode shape will be nice, but the gluing of them together, the merging of them will be bad. So you will have some kind of strange looking pieces that are, when you animate it looks really bad. So it's important that you have high quality sensors here as well as here. Just use the same kind of sensors everywhere. Then that's probably my recommendation. The next is that you need to put these in different locations where the modes that you are looking for, they have a good amplitude. And it might be difficult to find a single point in a single direction where all the modes you're looking for has a nice high amplitude level. And that's why we use several of these reference sensors here in order to be able to actually get the different modes, at least in one of these sensors every time we are doing a measurement. So use several of them, different locations in different directions. This is the most effective way of getting a nice mode shape in the end. So this is you could say, from a descriptive part or point of view, what we have to do now. Let me just show you here now. This is the plate I'm going to show you. I will switch my camera now and I will show you here what I have here on my table. I hope you can see it here. This is actually the plate that we see here in this slide here also. We are going to make 2 setups, 2 test setups. We are going to put 2 references here in these asymmetric points here. And then we are going to put the first 8 sensors that we want to use for the first setup, plus of course the 2 references here. So in total 10 accelerometers. We're going to put the first 8 up here. We do a measurement then, and then we will move it down here in this part here afterwards. So this is what we are going to do. And then we will end up using some different techniques afterwards in order to analyze the data here. So what I have to do now before I can start doing any testing, that is I have to switch to the software. And I have to now actually start making projects. So I will make an OMA project. And I will start making a small geometry here. I can probably insert a small rectangle here, like let's see this. I will now subdivide this into, so I have the points where I'm going to put my accelerometers. So now you can see I have a grid here that is 4 by 4. I can zoom in a little bit here. Then I can also add a few more points here. So I have something for my reference. Let's see that it's something like this. And here, that we will have these two references. So that's it. We will go now to the next task, because now we will need to prepare, you could say, two setups. We have to tell where the different sensors are located. And to do that, I will have to go to this task here we call assigned off information here. This is another setup task. I will then insert a new test up, and then I will insert 10 channels here, like this. The first channel here is the reference channel over here, the first location. The next one is the one I have over here. I simply drag them out, as you can see here. And then I have the rest organized like this, that we are simply putting them one by one here in this grid here, like this. Now we will take the second row here, like this. Let's get the rest here now. And finally, number 10, like this. So this is my first measurement, my first setup. This is the locations where I'm going to put the sensors and where you can see them actually on the camera. You can see that they are actually located here right now. Let's just make a small saving here of this one here. And then what I'll do now is I will insert an additional test setup, because we need another one for the rest of the structure. And the shortcut to do that is to right click here and then replicate what we have been doing here to copy as much as possible. So we don't have to do too much in the end. So I will just click this replicate here. It will now ask me which of all these 10 sensors that is actually or are the references. And I'll check the two first here. And now they will be inserted and connected automatically in the new setup, as you can see here. And then we just need to connect the rest of them here to the locations where we are going to put the sensors. Here it's of course important that we have an idea where we want to put our sensors, so that we are not just planning something here and then we are putting sensors in a completely different order when we start doing the testing, because then the result of that would be terrible looking mode shapes that will be difficult to find out what actually has caused them to look so terrible. But this is what we have to do in order to get started. Now we are ready to do an analysis or a measurement first, of course. And we do that by going here to the part where we can connect with some data acquisition system. And maybe you can see on the camera that I have a National Instrument data acquisition system connected. So I will choose this one here. And now we will communicate through a driver that has been installed from National Instruments. I can then find out that we have whatever sensors is now attached to it. These sensors are test sensors, so they have their own calibration information built in. So it's really convenient and easy to work with. And we have all these 10 sensors here, or accelerometers here, connected. As we can see, they're all green here. And then once we have found out that they are connected and so on, then we press OK. If it's something that doesn't have test information, these accelerometers, then we will actually have to define, you would say, the calibration factors for each of these sensors here. And that can be done by hitting this button here, and then you can then enter the calibration factor that you have from your calibration sheet that follows the sensor. But here it's automatically, because it's the test sensors we are using. And we simply connect here to the data acquisition task, which we see here. We have the 10 accelerometers connected here. This is what they are called if you look at it from a National Instruments point of view. What we like to do is we like to tell how the sensors we have defined in our project are linked to the hardware channels that we actually have available. And if it's the same kind of order, so that accelerometer, the physical accelerometer number 1, actually is sitting in the same location as the channel number 1 we were dragging out, and number 2 is also in the same direction, location and direction, then it's very easy, because we can make something we call auto-assignment. We can just tell everything is the same in the project and in the hardware definition we are using. And this is the case here, so I can easily get it to connect in this way, and we can see over here that everything is now green, which is very nice color in this case here. The next we can do is we can try to add a little bit diagrams here that allows us to see the running data. We can also try to connect something here called some SVD and PSD. That's some spectral density related diagrams. We can just take all of them like this. We should also configure, because we need to tell what sampling frequency we are going to use. If we sample low, we will not get so many modes. If we sample very high, we will get a lot of modes. So we have to find out what sampling frequency we would like to use. I will choose something from the list here. There are some available sampling frequencies that are coming from asking the data acquisition system, what do you have available? And I will just choose one of them here. I can also set up how I would like to measure. I can do manual. That means I start and then I stop when I want to stop. And then I'm in full control how much I would like to measure. But I could also try to use an interval recording. That means that I start in some way, and then after, let's say, 60 seconds, it will then stop automatically. I can also allow it to actually start automatically by enabling something we call triggered recording. So I can click this one here and say OK. And then I just say OK one more time here. Now I can just say that one of these sensors here is the trigger. When this sensor here starts detecting that there is something going on, we are going to measure an acceleration signal now at some reasonable level. Then the whole sequence of data acquisition will start. So we can just choose one of the ones, and we just use channel number 1, in this case here, to be our trigger. That's it. Now we can start it. And now you can see data coming in. It's running now in all these 10 channels here. And now you can see a diagram over here. And I'd just like to explain very briefly a little bit about this diagram here, because it's a really nice diagram that we use throughout ARTeMIS for spectral analysis, you could say. Let me just go back to this presentation here. We start out from measurements that are recorded in time domain. For each channel, we can calculate something called a spectral density function. That's one you can see like this. It will look like this for channel number 1, you could say. We can make a similar one for channel number 2. It will look something like this, and channel number 3 like this. We can also make something between channels. So we can actually create a cross spectral density between channel number 1 and 2. It will look something like this. And it's basically equivalent to this one here, more or less. And in this way here, we can get different kinds of cross spectral densities calculated between the different channels. In total, if we have 3 channels, we will have 9 spectral densities functions to work with. 3 auto spectral densities, and then 6 cross spectral density functions. You can imagine that we now try to look at a specific frequency. It's stippled here with a stipple line is here. So we grab that value in all the 9 functions here. We stuff it into this matrix here. That is now a 3 by 3 matrix. Then using the singular value decomposition, we can now decompose it so that we get a diagonal matrix with singular values. This one here is the first singular value. This is the number that you will then see here. The second singular value is slightly smaller. That will be the one that you see here. And then the last one is the one you see down here, the smallest one of the three. They are always organized in this way here, which means that you will have a kind of a continuous curve of one color on top of each other like this. This is the singular value decomposition diagram. It allows us now to linearize, you could say, a quadratic problem. We have 9 diagrams to look at if you look in this domain here. But now we come back and we actually have one diagram with 3 values corresponding to the 3 channels that we were measuring. So what you can see here now is how this diagram looks depending on the type of structure that we have. If you have a non-symmetric structure that we are working with now, you can actually see that all the different modes of vibration show up here as a single peak in this diagram here. This is when we have what we call well-separated modes. You can also, we can also have these types of peaks here, where we have. Let me just switch my camera here first of all. We can also have this one here. This is one I've zoomed in here very closely together. We can have 2 modes. They are not at the same frequency, but they are close together. So we call it closed space modes. But again, this can happen if you have a symmetric or non-symmetric structure that has more or less the same dimensions. So this is one way you can, the diagram will look. You can also have, when you have a symmetric structure, then you get them lying at exactly the same frequency. So you have 2 singular values, like you can see here, popping up to the same frequency. This is clearly when you have something that is, you are testing that is symmetric. Here we is, you would say, this small structure here that has the 2 dimensions here that are the same. But it could also be a circular structure where you will actually have many of these singular values popping up, because the circular structure, in principle, gives you infinite amount of modes at the same frequency. So this is some of the things you can get out of looking at the singular value diagram. Other things you can see is also the quality of your measurements. If it looks like this, it's not so good. If it looks like this, it's really nice. When it looks like this, I think actually we can go and check it out here on our structure here. You can see something, it more or less looks like this here in our analysis or our testing we are doing now. But when it looks like this, it means that you have a noise floor that is really high compared to where the dynamics of the structure is actually located. So the difference between, you could say, the highest peak and then the noise floor, that is where the flat start here down here, is not a lot of dBs. Maybe there's only 30 dBs here or something. It's not enough. If it looks like this, it's going to be difficult to analyze. If it looks like this, where you have the flat part down here, and now there is a distance between this part here and then the peak here that is perhaps 70 dB, then it's much better and much easier actually to analyze. So by looking at the diagram and seeing the difference between the 2 here, this allows us to see if it's going to be difficult or easy to actually analyze the data. We should aim for this. If it looks like this, we should try force some more excitation in, or in some way modify the hardware, the equipment, making it more sensitive to the level of vibration we have, so that we can get this noise floor lowered even more. Okay, another thing we can look at, we are not going to discuss it today, but that is if we have something that is rotating, this is a shaker that is shaking this one with a sinusoidal excitation, we get some distinct peaks here at the rotational frequencies that are excited on the structure here. So this is another thing we can actually get out from the SVD diagram. Finally, we can also look at if it looks like this. So we have some nice smooth peaks up here, but there's also something here that looks a little bit strange. It's very kind of scattered behavior. This is normally an indication that at least one of the channels is not behaving so nicely. It can be that you have a loose sensor. So it's not really connected to the structure. It can also be loose to the you would say to the cable. It can also be the cable that is more or less broken, or the sensor can also have dropped off when you're doing the test. So now it's just hanging, measuring nothing. Then you will actually also see this kind of behavior here. So it's not something you should ignore. You should really go back, look at your sensors, look at your data acquisition system, check out if everything is connected properly, because it's a clear indication that it's not. And if you don't do anything about it, you're going to have troubles analyzing it, and you're going to have at least one node-shaped component degree of freedom that will be bad. It will be zero or noise that you'll be estimating for that one. So make sure that this is not going to happen. Then we get to the point where we are looking here at how many inputs we have. Actually, you can see that from the SVD also. If you have only one line here that is really at a high level, that indicates that you have one input, one particular heavy or significant input. If you have two of these, it will look like this. If you have multiple, it looks like this. Let's try and go to the software. Now I'll switch my camera back to the other one so you can see what I'm doing here. Because if I now try to take a pencil here, and now I will just hit this point here. I can hit it. Now you can actually see that we have the blue line is growing up now. It's becoming quite significant compared to the other ones, indicating that there is a single input that is exciting this structure here now. Now I like to become a drum player here. Now I will estimate, or I will hit two different at the same time, and then we should see the red one coming up also. As you can see here now, slowly but steadily, it's coming closer and closer to the blue one. It's not so easy actually as it may look. But this is the way you can see how many input do you have. The more input you have, the more of these singular values will now be actually coming up. And this, of course, brings me to how we should now test if we want to produce a diagram with multiple inputs. What I can do is I can simply do like this. If I now hit all randomly places on this structure here with my pen, you can see how all the other singular values are now actually also popping up and helping us actually to much better understand the dynamics of this structure here, and of course also helping the analysis to become better. Because it's not only a visible thing that it looks better, it is actually also for the analysis that we're going to do later on that will be better. So we'll be using this kind of technique here in order to do the measurement. I will now start the measurement. Now it's waiting for me to start triggering something to trigger, and then it will record for 1 minute. So let's try that. I don't know if you heard, there is a electronic voice saying that it was triggered, and now you can see that the clock is running. So we will count up to 1 minute now, and then we will let me know that it's finished with this recording here. So we will just carry on like this for a while, 30 seconds more, I guess. And you can see I'm just hitting as randomly as I can, because this is how I can in some way simulate Mother Nature. That will also just excite a civil engineering structure, for example, completely randomly, different locations with different types of excitation. It can be wind together with waves, and there can also be micro tremors from the ground that is affecting at the same time. So all kinds of ambient excitation that we cannot control. This is the first measurement. The way to now go to the next measurement is that I have to tell ARTeMIS now that I'm going to the next one. I simply switch here like this. Now it says setup number 2 here. And of course I have to go here now, and I have to move the sensors, because I'm going to now measure on the second setup location here. So I will be moving these sensors here, and this is where we have to be a little careful moving them correctly so that we do not end up with a strange looking mode shape. Let me see here. We will do like this. So now I just need to have a little bit of room for tapping here. Now I will start again the recording. So I put it on. This is just to turn on the acquisition, and then I can start the recording. And now it's waiting again that I'm tapping because I'm using this triggered recording. So then I start, and then we start measuring like this. And then we have to wait a minute in order to see what's going on. And you can see I'm trying to hit as many places as possible without actually hitting the accelerometers, because that would not be very nice, because it will give us some overloads that are creating a lot of noise, white noise actually, that will then actually make the analysis bad, basically. If you get the kind of outliers from, let's say, that we hit one of these, we should actually do some kind of removal of these outliers before analyzing the data, because otherwise we will have severely amount of white noise put into this analysis here. So this is basically what we had to do. I can save the recording here now and switch the camera back again here. And now we actually finished with the recording. The raw measurements can be viewed here in this manage measurement task here for the two setups. Here I just enabled by default 4 channels. We can see for the first setup here, and it looks very nice. We have been impacting all the way. There's no places where there's nothing happening, and the same for the second setup. That looks okay too. So this way we can now work with the raw data in this task here. And then we can switch to the analysis part. Here we go first to a task where we have to, you would say, do something with the measurements that we have now measured. We have to process them in different ways, because the different methods we are using require different kind of processing of the raw data. We can just actually hit the button here. We use the default settings already, and then we start actually analyzing the raw measurements here. Now it's doing the most, you could say, basic that is required. You can do all kinds of additional, say, filtering and other things. But normally I would always start with the default setup and process it with the default settings, because you don't know what you have before you have seen actually spectrals like this and so on. So it's important to start without any filtering or any other things. And then you can always go back again if you don't like what you see here, and then reprocess the data. But here it looks quite good. I think we have all these different peaks here of the different modes, and this indicates all the modes that we can find for this particular structure here. If I go back to my little slide here, then I have a single slide here that just explains the type of estimators we have in the software. We have some that is working in frequency domain. They are derived from something called frequency domain decomposition. That is basically that we do a singular value decomposition of the spectral densities that I already have shown. And based on this, we can now extract frequency, and for some of the methods also damping, and of course the mode shape. So this is what we do in frequency domain. We can try and go back to the software and just try it out. If I go here to estimation, I can choose, let's say, EFDD, that is one of the frequency domain methods. this one here, if I need to make a peak picking automatically, sorry, manually. And I can do that simply by clicking this button here, and then I can start clicking my way through here, as you can see here, like this. And then I can extract every time a mode. I get a mode shape, as you can see up here. I get a natural frequency here, and I also get this damping ratio, as you can see. So this is for each of these modes, I get this set of parameters that we talked about in the beginning. And there are different methods available. If we expand here, you can see I have 3 different frequency domain decomposition methods. The first one only gives us a mode shape and a rough estimate of the natural frequency based on what we can read on our frequency axis. The second one is the one I'm using here that actually estimates frequency damping and mode shape by some regression. And then there is also another one that is working in frequency domain that we can also use in a similar manner to extract frequency damping and mode shape. This is, you could say, the frequency domain methods we have. We also have these stochastic subspace identification methods. They work in time domain directly on the time series measurements. The idea here is that we are going to make a so-called stabilization diagram where we are estimating a range of models from a model order 1 and then up to a maximum order, extracting the modes of each of these models here and presenting the frequencies of those in this diagram here. Every time we have this kind of vertical red list of dots here, it shows us that we have a stable mode. We have the same mode appearing in all these different models here. And based on that, we can now extract all of these frequencies, damping ratios, and mode shapes also, and then average them together to get a single global mode estimate. And that's the one we'll then get over here. So you would say the first one we have here in the list here is actually an average of everything that is going on here. All the red crosses here, you could say, are the ones that are in some way are included in that average to give us an average frequency, average damping ratio, and also an average mode shape, as we can see up here. And this tool here is I'm using here is called SSI, and I'm using one of them, the most advanced we have, that estimates not only the natural frequency, damping ratio, and mode shape, but also uncertainties of these. So we get a mean value of the frequency here, but we also get a standard deviation estimated, for example, here, and the same for the damping ratio, as you can see. Similar can be obtained for the mode shape, but that's an additional step we have up here if we want to do that. So this is how it works, and this method here works per setup. So I actually have this kind of stabilization diagram here for each of the 2 setups. This is setup number 1. So here I have another one because I need to fit models for each of the positions I have placed the sensors for each of these setups here in order to be able to do it correctly. And then in the end, things are put together, and we are doing some merging that is happening graphically up here in this level here. We are finding a mean value of what's going on in the first setup and a mean value of the second, and then we are merging these 2 together. So we are getting a mean value of everything when it comes to frequency and damping, and we are getting a mode shape that is put together based on the reference information we have. So this diagram here helps us to see which of all the modes that has been merged together properly. And we can actually see that we have the 2 closely spaced modes. We have troubles here actually. We have not been able to merge it together automatically. So here we have to help the software. You can see there are a dot here and there is another dot down here. They are not put together with a line. So I actually have here to help it simply by placing this line here on top of the 2 and then double click like this. And then do exactly the same here for the other 2. And in this way, I merge them together. This happens if we have multiple setups and we have modes that are very close. But if there is some kind of, difference in frequency or mode shape, between the two setups, then it fails to do it automatically. And in our case here, it's because we've been moving some masses. The sensors are having some mass. We are moving them from one part to another part, and this causes these troubles here. But once we have done everything here, we can actually move to a validation. Here we can actually compare what we have been doing with one of the methods and the other. I have some of the methods, not all, the most estimate I can see for FDD, but we can, for example, try to select two modes and put them on top of each other. So now I'm animating the mode, the first mode from eFDD and the first mode from UPCX, the SSI method, together. And you can now see how the mode shapes are basically the same. There is a little bit of flicker in the colors because they are not completely agreeing on the phase, you could say, between the two. But the blue is the eFDD and the SSI is the red mode shape we have here. Up here we can see something we call the cross MAC. This is a diagram that shows the correlation between the mode shapes of the SSI and the mode shape of the eFDD modes. And you can see the ones that has been found, in this case, all seems to agree very nicely. They look the same as we can see here on this diagram here. So this is some of the functionality we have for comparison of the different estimates we have available within the project. You can also imagine you can actually import modes from other tools or other projects and compare between those and then what you have inside this particular project here. So this is very shortly a little bit about what we can do of estimation inside the software with the different techniques we have available. There are many, as you can see, but I only showed two of them due to the shortage of time here. And then let me just finally come with some remarks here about our platform. What I've been showing you here is what we call the ARTeMIS Modal Pro. This is the part or the version of the software that includes all the different operational modal analysis estimators we have available. There are other downscale versions of ARTeMIS that has fewer estimators available, but all of them you can actually connect with hardware, different types of hardware acquisition systems that we support, and these are the ones that we show here. I use the National Instruments in this case here. This requires some kind of plug-in, an additional license that allows you to open up for the measurement or data acquisition parts for projects. If you don't want that, you can also just create a file with your recordings in time domain, and then you can upload it through the managed measurement task inside the software. And we support more than 20 different file formats, so there should be one that can support whatever measurement tools you are using. Today we showed a little bit of how to do multiple test setup testing, and of course we also support if you only have a single one. And it's the same platform. There's nothing additional license that you have to acquire in order to get single or multiple setups running. So it's quite easy and convenient. If you also have a need for experimental modal analysis, or perhaps structural health monitoring based on vibrations, we have additional plugins that I've been talking about in a previous webinar last month, I think it was, or 2 months ago. And then I'll also be talking in February about SHM. In this case here, we have been talking about operational modal analysis, where we have different techniques available. We have up to 8. If it's multiple setups, there are 8 different techniques available in the Pro version. We like to use multiple techniques of different kind and then compare things using the validation task to make sure that we are actually getting the same kind of results when we are using different tools. So that's why we have these different tools running in parallel, you could say, in a project like this. And I showed already the validation features that we have available for this. So thank you. The only thing I'd like to just add is that you can look at some different videos. This presentation will go to our YouTube channel as well. But there are many others, instruction videos and webinars and so on that you can have a look at there. And of course, our website is also full of interesting information. We have a literature parts where all the different scientific papers that we have been participating in or writing ourselves over the time, they are available for downloads. And there's also, of course, the software available that you can try it out. For the ones that would like to have more detailed, you could say, training on the software, then we are giving an annual user training course. It happens here in Denmark, in our headquarters here. And it happens in April next year. On 15 and 16 April, there will be this user training course. And you can go to our website if you're interested, and you can download a registration form there that you should fill out. And then finally, there is this next webinar here where we are going to present our structural health monitoring tools we have available in ARTeMIS Modal. There will be some exciting new stuff available that we have not shown before at this time here. So I hope to see some of you at that time. But otherwise, thank you very much for watching.